Welcome to our comprehensive exploration of super-resolution microscopy, where we'll discover how scientists break the supposedly unbreakable diffraction limit. For over a century, physicists believed there was a fundamental limit to how small we could see with light microscopy. Today we'll explore how modern techniques shatter this barrier. Let's begin by understanding the classical diffraction limit, established by Ernst Abbe in 1873. The Abbe diffraction limit states that the minimum resolvable distance d equals wavelength lambda divided by 2 times the numerical aperture. For visible light at 500 nanometers wavelength with a high numerical aperture objective of 1.4, we get approximately 180 nanometers as our resolution limit. When 2 point sources are closer than this limit, their point spread functions overlap completely, making them indistinguishable as separate objects. The Rayleigh criterion provides another formulation. The angular resolution equals 1.2 2 times wavelength divided by aperture diameter. But why does this limit exist at all? The answer lies in the wave nature of light and unavoidable diffraction through the objective lens. Let's dive deeper into the physical mechanisms that create this seemingly insurmountable barrier. The airy disk pattern shows how a point source spreads into a characteristic sinc-squared intensity distribution with a central peak and surrounding rings. High spatial frequencies, which encode fine details, decay exponentially as evanescent waves and never reach the far-field detector. Evanescent waves decay exponentially with distance z, where kappa depends on the transverse wave vectors exceeding the free space wave number k0. The crucial question: if this is a fundamental physical law, how can modern techniques possibly overcome it? The answer lies in clever tricks. Our first super-resolution technique is STED, or Stimulated Emission Depletion Microscopy, developed by Stefan Hell, who won the 2014 Nobel Prize. STED uses 2 laser beams, an excitation beam to excite fluorophores, and a donut-shaped depletion beam that forces excited molecules back to ground state everywhere except the center. The effective resolution instead is lambda over 2Na times the square root of 1 plus I over I saturation, where I is the depletion beam intensity. By cranking up the depletion laser power to very high intensities, STED microscopes routinely achieve resolutions of 20 to 30 nanometers, nearly 10 times better than diffraction limit. The saturation intensity depends on photon energy, fluorophore cross-section sigma around 10 to the minus 16 square centimeters, and excited state lifetime tau. The crucial insight is that stimulated emission introduces a nonlinear relationship between intensity and fluorescence, allowing us to confine emission to an arbitrarily small volume. Photoactivated localization microscopy and stochastic optical reconstruction microscopy take a completely different approach based on single molecule localization. The strategy is to activate only a sparse subset of fluorophores at any given time, then precisely localize each one by fitting its point spread function. The localization precision equals the PSF width divided by the square root of n detected photons. With thousands of photons, we can localize to a few nanometers. In practice, with modern cameras collecting 1,000 photons per molecule, researchers achieve localization precision of 10 to 20 nanometers. By acquiring tens of thousands of frames, each with different molecules activated, we build up a super-resolved image point by point. This technique requires special photo-switchable fluorophores that can be toggled between bright and dark states with different wavelengths of light. Let's examine the mathematical foundation that allows such precise localization despite the diffraction limit. The point spread function is approximated as a 2D Gaussian, with center at x0, y0, and width sigma determined by the diffraction limit. We fit this PSF to the measured data by minimizing chi-squared, the sum of squared differences between data D and model PSF weighted by noise. Maximum likelihood estimation allows us to determine the molecule position with precision much better than a single pixel, typically reaching 1/10 of a pixel or better. The full expression for localization precision includes the PSF width S, pixel size A, detected photons N, and background B. The second term shows noise degrades precision at low photon counts. With optimized conditions collecting 5,000 photons, state-of-the-art systems reach astonishing 5 nanometer localization precision. Now let's explore techniques that directly access the evanescent near field, capturing high spatial frequencies before they decay. Near-field scanning optical microscopy uses a sharp probe placed within nanometers of the sample surface, capturing evanescent waves before they decay. The resolution in near-field microscopy is determined by the aperture diameter, not the wavelength, achieving resolution below 100 nanometers, even with visible light. Total internal reflection microscopy generates strong evanescent fields at an interface, selectively illuminating only molecules within about 100 nanometers of the surface. The evanescent wave penetration depth depends on wavelength, refractive indices, and illumination angle theta, typically giving 50 to 200 nanometer depth. Plasmonic nanostructures provide another route to superresolution by concentrating light into nanoscale hotspots. When two gold nanoparticles are brought close together, the gap between them creates an intense electromagnetic hotspot, with field enhancement factors exceeding 1,000. The field enhancement scales approximately as the ratio of particle radius r to gap size d, multiplied by the dielectric contrast between metal and surrounding medium. With gaps as small as 1 to 2 nanometers, these plasmonic antennas create hotspots comparable to single-molecule dimensions. The effective mode volume can be squeezed to a cube with sides d over 10, where d is the gap size, far smaller than the diffraction-limited cubic wavelength volume. These plasmonic hotspots enable single-molecule spectroscopy and ultra-sensitive chemical sensing, detecting individual molecular binding events in real time. Structured illumination provides yet another approach, using patterned light to encode high frequencies into lower-frequency moire patterns. By projecting sinusoidal fringe patterns onto the sample and capturing multiple images with different pattern positions and orientations, we extract hidden high-frequency information. The observed intensity is the product of sample structure and illumination pattern. This multiplication in real space creates sum and difference frequencies in Fourier space. In Fourier space, the pattern shifts high spatial frequencies kx plus or minus k0 into the observable range, effectively doubling the resolution. Standard structured illumination gives a factor of 2 resolution improvement, reaching about 100 nanometers, while nonlinear variants push this even further. What are the absolute best resolutions achieved today? Let's look at record-breaking results. MINFLUX achieves 1 to 5 nanometer resolution by minimizing photon flux at the molecule position. DNA paint reaches 5 to 10 nanometers through transient binding. STED typically achieves 20 to 30 nanometers. MINFLUX resolution scales as L, the pattern size, divided by square root of photon number n. With careful optimization, this reaches the astonishing 1 nanometer regime. 1 nanometer resolution means we're approaching atomic scale imaging with ordinary visible light, something that seemed impossible just decades ago. But these techniques aren't magic. Let's discuss practical challenges and fundamental trade-offs that researchers face. There's an inherent trade-off between resolution and speed. Palm and Storm require thousands of frames, taking minutes to hours for a single image. High laser intensities needed for STED cause phototoxicity that can damage or kill living cells, limiting long-term live cell studies. A typical Palm experiment with 10,000 frames at 50 milliseconds each requires over 8 minutes of continuous acquisition. At nanometer resolution, even tiny thermal drift of the microscope stage or sample becomes a major problem requiring active stabilization systems. Without drift correction, sample motion during acquisition blurs the final super-resolved image, requiring fiducial markers and computational correction. Why does all this matter? Let's explore how super-resolution microscopy revolutionizes nanotechnology research. Superresolution allows researchers to watch individual motor proteins like kinesin walk along microtubules, step by 8 nanometer step. By localizing the motor protein position in consecutive frames, we can measure its 8 nanometer stepping pattern and mechanistic details of force generation. Cell membrane proteins organize into nanoscale clusters and domains that control signaling. Superresolution reveals their spatial organization and dynamics. In quantum dot research, superresolution enables counting the exact number of fluorescent molecules or defects within individual nanocrystals. By comparing total fluorescence intensity to single molecule intensity, corrected for shot noise proportional to square root n, we determine molecule number with statistical confidence. DNA origami creates programmable nanostructures, Superresolution microscopy validates designs by imaging the placement of fluorescent labels at specific sites. Let's address a fundamental question. If we've beaten the diffraction limit, does that mean it wasn't a real limit after all? The diffraction limit is absolutely real for passive linear imaging. What these techniques do is add information or constraints beyond simple intensity measurement. Superresolution techniques add information: temporal sparsity in palm, nonlinear depletion in STED, or spatial structure in SIM. This extra information bypasses the classical limit. However, you still cannot violate fundamental information theory bounds. The amount of information extractable is limited by photon statistics and signal-to-noise. The Fisher information quantifies how much information the data contains about parameter theta. This sets fundamental bounds on parameter estimation precision. Can we do even better? What are the ultimate quantum mechanical limits to resolution? The quantum Kramer-Rao bound states that localization precision is fundamentally limited by 1 over square root of detected photons. No technique can beat this. If we could collect 100,000 photons from a single molecule without bleaching, the quantum limit would be approximately 0.3 nanometers, approaching interatomic distances. Quantum entangled photon pairs might provide additional advantage through quantum metrology protocols, though this remains mostly theoretical for microscopy. With m-photon entangled states, precision could potentially improve by an additional factor of square root m, the Heisenberg limit. Modern approaches increasingly combine optical techniques with sophisticated computational algorithms. Deep neural networks trained on high-quality datasets can dramatically accelerate reconstruction, turning hours of computation into seconds. The pipeline feeds raw microscopy data through a trained neural network that outputs super-resolved images, learning complex relationships between diffraction-limited inputs and ground truth. Training minimizes a loss function, combining L2 difference between predicted and true images, plus a regularization term R that enforces physical constraints like sparsity. Compressed sensing theory proves that sparse signals can be perfectly reconstructed from far fewer measurements than traditional Nyquist sampling requires. Let's work through a concrete example: imaging the protein shell of a virus particle using storm microscopy. Consider an HIV virus particle, approximately 50 nanometers in radius, decorated with envelope proteins we've labeled with photoswitchable fluorophores. The virus has roughly 10 envelope protein spikes, spaced about 15 nanometers apart, well below the 200 nanometer diffraction limit. With conventional microscopy, we see only a single fuzzy blob about 200 nanometers across, revealing nothing about protein organization. But with STORM, acquiring 20,000 frames over 15 minutes, we reconstruct individual protein positions, revealing the discrete spike distribution. With 3,000 photons per localization, we achieve about 3 nanometer precision, more than sufficient to resolve 15 nanometer spacings. Looking forward, what are the major challenges and opportunities for the next generation of super-resolution techniques? The Holy Grail is combining nanometer resolution with millisecond temporal resolution to watch nanoscale processes in living cells in real time. Most techniques work in 2D. Extending to full 3D superresolution throughout thick samples remains challenging due to aberrations and light scattering. The axial resolution delta Z is typically several times worse than lateral resolution delta X, creating elongated point spread functions in 3D. Biological processes involve multiple interacting components. Simultaneous multicolor superresolution with independent labels remains technically demanding. 3-color superresolution requires careful spectral separation, compatible fluorophores, and often sequential acquisition, multiplying acquisition time. State-of-the-art superresolution microscopes cost hundreds of thousands of dollars. Can we democratize this technology? Commercial STED microscopes range from $400,000 to $800,000, requiring specialized pulsed lasers and precise optical alignment. In contrast, STORM can be implemented as an add-on to existing microscopes for under $50,000 using standard continuous wave lasers. Open-source hardware and software projects are making superresolution accessible to labs with limited budgets through do-it-yourself implementations. The most powerful approaches combine superresolution with complementary techniques from multimodal imaging. CLEN combines fluorescent superresolution with electron microscopy's nanometer resolution and ultrastructural detail. By imaging the same structure with both fluorescent superresolution and electron microscopy, researchers get molecular specificity plus ultrastructural context, Combining super-resolution fluorescence with atomic force microscopy reveals both molecular identity and precise three-dimensional surface topography. Let's summarize the key equations that govern super-resolution microscopy. The classical Abbe limit versus the STED resolution that improves with depletion intensity. Localization precision scales as PSF width over square root photons, approaching the quantum limit at high photon counts. Structured illumination doubles resolution, while evanescent waves decay exponentially with characteristic penetration depth. Super-resolution microscopy represents one of the great triumphs of modern biophysics and nanotechnology, enabling scientists to study the nanoscale world with unprecedented clarity and precision.